Ground fault circuit interrupters, or GFCIs, are designed to lock out after a certain number of faults. The National Electrical Code requires GFCIs to lock out after 30 milliseconds worth of cumulative fault current. This equates to approximately 6 faults at 5 mA, 3 faults at 10 mA, or 1 fault at 30 mA. The purpose of the lockout mechanism is to prevent the GFCI from repeatedly tripping due to transient or nuisance faults. It provides an opportunity to identify and correct the underlying issue causing the faults. Using GFCI plug-in testers is recommended as a way to test GFCIs. These testers simulate a fault to verify that the GFCI is functioning properly. To test a GFCI using a plug-in tester, firstly, insert the tester into the GFCI outlet. Secondly, press the test button on the tester. Thirdly, the GFCI should immediately trip. Fourthly, press the reset button on the GFCI to restore power. Fifthly, press the reset button on the tester. Sixthly, the GFCI should stay powered on, indicating that it is functioning correctly. If the GFCI does not trip with the tester, it is likely faulty and should be replaced. Some GFCIs may have a reset life where they will eventually lock out permanently after a certain number of resets. The National Electrical Code requires GFCIs to be installed in specific locations such as bathrooms, kitchens, and outdoor areas. It is important to test GFCIs regularly to ensure they are functioning properly and providing protection against electrical faults. A ground fault circuit interrupter, or GFCI, is a crucial safety device designed to protect individuals from electrical shock. It works by monitoring the current flowing in a circuit and quickly interrupting the power if it detects a ground fault, which occurs when current flows through an unintended path, such as a person's body. The sensitivity of a GFCI is typically set to trip when it detects a current imbalance of 5 mA or more. This rapid response is vital because even small amounts of current can be dangerous and potentially fatal. The National Electrical Code mandates the use of GFCIs in various locations where there is a higher risk of electrical shock, particularly in damp or wet environments. These locations include bathrooms, kitchens, outdoor outlets, garages, and near swimming pools. The purpose of this requirement is to minimize the risk of electrocution in areas where people are more likely to come into contact with water or grounded surfaces. GFCIs are available in several forms, including receptacle types, circuit breaker types, and portable types. Receptacle GFCIs are installed in place of standard electrical outlets, providing protection at that specific location. Circuit breaker GFCIs, on the other hand, are installed in the electrical panel and protect the entire circuit. Portable GFCIs are designed for temporary use and can be plugged into regular outlets to provide temporary ground fault protection. Testing GFCIs regularly is essential to ensure they are functioning correctly. The recommended procedure involves using a built-in test button on the GFCI or a separate GFCI tester. When the test button is pressed, it simulates a ground fault, causing the GFCI to trip and cut off power to the circuit. If the GFCI fails to trip during the test, it indicates that the device is faulty and needs to be replaced. Regular testing helps to identify any potential issues and ensures that the GFCI is ready to protect against ground faults when needed. In addition to regular testing, it is also important to understand the limitations of GFCIs. While they provide excellent protection against ground faults, they do not protect against overloads or short circuits. Overloads occur when too much current flows through a circuit, while short circuits happen when there is a direct connection between two conductors with different potentials. These conditions can cause overheating and potentially lead to fires. To protect against overloads and short circuits, circuit breakers or fuses are used in conjunction with GFCIs. Circuit breakers and fuses are designed to interrupt the flow of current when it exceeds a safe level, preventing damage to the electrical system and reducing the risk of fire. Proper installation and maintenance of GFCIs are crucial for their effectiveness. It is important to follow the manufacturer's instructions during installation and to ensure that the GFCI is properly grounded. Grounding provides a safe path for fault current to flow back to the source, allowing the GFCI to detect the imbalance and trip the circuit. If the GFCI is not properly grounded, it may not function correctly, and the risk of electrical shock increases. Furthermore, it is important to protect GFCIs from physical damage and exposure to extreme temperatures or moisture. Damage to the GFCI can compromise its ability to function properly, while exposure to harsh conditions can accelerate its deterioration. Regular inspection of GFCIs for any signs of damage or wear is recommended, and any damaged GFCI should be replaced immediately. Understanding the principles of ground fault protection is essential for electrical safety. A ground fault occurs when current deviates from its intended path and flows through an unintended conductor, such as a person's body. This can happen if insulation on a wire is damaged, allowing the current to leak out and find an alternative path to ground. When a ground fault occurs, the current can flow through a person's body, causing an electrical shock. The severity of the shock depends on the amount of current flowing through the body and the duration of the exposure. Even small amounts of current can cause muscle contractions, difficulty breathing, and potentially cardiac arrest. GFCIs are designed to detect these ground faults and quickly interrupt the power supply, preventing serious injury or death. The working principle of a GFCI is based on the detection of current imbalance. A GFCI contains a sensing transformer that monitors the current flow through the hot and neutral conductors of a circuit. In a properly functioning circuit, the current flowing through the hot conductor should be equal to the current flowing through the neutral conductor. However, when a ground fault occurs, some of the current leaks out and flows through an unintended path to ground. This creates an imbalance between the current in the hot and neutral conductors. The sensing transformer detects this imbalance and triggers the GFCI to trip, interrupting the power supply to the circuit. The entire process happens very quickly, typically within a fraction of a second, minimizing the duration of the electrical shock. GFCIs are designed to be highly reliable and are required to meet strict performance standards. These standards specify the maximum amount of time allowed for the GFCI to trip under various fault conditions. The standards also require GFCIs to be resistant to false tripping caused by transient voltage surges or other electrical disturbances. Regular testing and maintenance of GFCIs are essential to ensure they continue to meet these performance standards and provide reliable protection against ground faults. In addition to residential applications, GFCIs are also widely used in commercial and industrial settings. They are commonly found in construction sites, factories, and other workplaces where there is a higher risk of electrical hazards. The National Electrical Code provides specific requirements for the installation and use of GFCIs in these settings to ensure the safety of workers and the public. Proper training and education on the use of GFCIs are essential for all individuals who work with or around electricity. Workers should be trained to recognize the hazards of ground faults and to understand the proper procedures for testing and maintaining GFCIs. They should also be aware of the limitations of GFCIs and the importance of using other safety measures, such as wearing appropriate personal protective equipment. By promoting a culture of safety and providing adequate training, employers can significantly reduce the risk of electrical accidents and injuries in the workplace. In conclusion, ground fault circuit interrupters are essential safety devices that protect individuals from electrical shock by quickly interrupting the power supply in the event of a ground fault. They are required in various locations where there is a higher risk of electrical shock, and regular testing and maintenance are crucial to ensure their proper functioning. Understanding the principles of ground fault protection and the limitations of GFCIs is essential for electrical safety in both residential and commercial settings. By following the recommendations of the National Electrical Code and promoting a culture of safety, we can minimize the risk of electrical accidents and injuries and create a safer environment for everyone.